All right, okay. I think it's my turn to go now. Good morning, everyone. Thank you for having me here today. I'm going to be talking about the Three Musketeers. I'd say about a 3 out of 5 for original name, but maybe a 1 out of 5 for context. So, what I'm going to be talking about today is Java, Docker, and memory. And with memory, you can always basically include CPU. So, if you know the Three Musketeers, there were 4 of them. Yeah, it's not so it's name. It's okay. I'm Greg. I'm a technical lead at Intellect. I am an electrical engineer by training, but I am a software engineer by profession. I've worked on a number of projects, but at the moment, I'm at Standard Bank. I'm working in the payment space, and we are basically modernizing the whole payment area. If you guys hear anything about RPP, don't look at us, look at someone else. Today, I'll talk about Java, Docker, memory, and CPU. So Java, obviously, is Java conference, but Docker is definitely becoming a preferred way of deploying applications. Let's start straight into it. What are resources? Why do we care about resources? Why should you care about resources? Well, CPU, how much CPU does your application need? How long is a piece of string? Kind of hard to measure. What happens if you have too much? What happens if you have too little? Spoiler alert, if you don't have enough CPU usage, your application won't run. And if you have just enough, well, you might end up with some kind of like thrashing situation. Your application just is too slow to actually get anything meaningful done. Memory, on the other hand, well, it's a bit different. It's a little bit of a strange one. If you have enough memory, adding more memory doesn't make the application faster. And I want to show you some of these results as we dive into this. But what I want to do today is I want to show you guys how you can have a look at your application and see how much CPU and how much memory you actually need. Why is this important? Well, if you're running maybe on a virtual machine or an application server, maybe you're running a massive monolith, perhaps an older application, you have to provision these applications. You have to provision a VM, and they're going to come ask you how much memory. And if you're anything like me, you're going to be 1 gig, 1 CPU. That sounds like a good number, and then we'll see if it's enough afterwards. And that was kind of okay when we were dealing with VMs, because maybe we had 1 or 2 instances of the application running. You may be overspec by 50%, wasn't too bad. But, well, we're moving on to Kubernetes, and we're using microservices. Your applications are much smaller, maybe they don't need as much. So if you overspec by 50% and you're running like 4 instances, well, that adds up very quickly. You could be running 2 or 3 more instances with just the wasted resources that you have. And so fine, that's maybe your client's problem because they're the ones that pay the bill. You're just the developer, we don't have to pay for that, so that's fine. But Kubernetes has other nice things with monitoring and autoscaling. If you get these resources wrong, your application won't be able to autoscale automatically, which means that, come on Friday, you're going to be there like more parts please, but if you use your resources right, that can happen automatically in the background, and you could be at the shop figures. So I'm going to focus on Kubernetes today because I think that is the most generic platform that most of us are deploying to these days. But the same principles can be applied to virtual machines or maybe whatever else you're deploying to. Kubernetes has a concept of requests and limits when it comes to resources. You have a request, you ask the part that you're going to be deploying, can I have some CPU and some memory? The way that Kubernetes interprets requests is it's a guarantee. You will have at least this much available to you. This is good because now your application can run, but it's not a hard limit because you can't actually go over your resource request. So if there's a little extra capacity there, maybe you can float over a bit. That's quite nice. Your limit on the other hand is a hard limit. It's in the net. That's how much you are allowed to use. This is important to know because with Java, if you use more memory than what your limit allows, your application will get killed. Out of memory. And if your application just dies, that's a pretty second situation to be in. CPU, it's not as harsh. You just get limited to that amount of CPU. But if you set that value too low, your application is going to run, you can just stuff up. The interesting thing, though, is depending on your Kubernetes platform, they may interpret these values as the same. Some of them don't actually have a full out implementation for limits. It'll just use your request amount for both. So to keep it simple, I think to just use the same data for both of these. And in the context of a Java application, the JVM, then it's a bit simpler to understand as well. So, just right. We could spend probably hours and weeks and months and years fine-tuning this application to be the most performant application. But, that could take way too much time. So what we want to do is we just want to find just right. We don't have too much memory. We don't want to have too little memory. We just want a pragmatic approach. Something that's good enough. Something that's not going to take us years and years to try and refine. So we're going to take an application. We're going to assume it just works. And we're going to find what is good enough. Good enough for it to run. Good enough so that we can get good responses. And good enough that we're not wasting resources. So we need to define what we're going to measure. What is it that makes this application good or useful? Well, it's generally what it does for your client or the customer on the other hand. So if you're talking about an API, you're talking about response times. Your user of the application doesn't care that you're using 80% of your memory. They only care that you can respond in a second. Typically, we talk about 1 subsecond response times. How are we going to go about measuring that? Well, so we're going to hit it, API request, and we're going to measure our response time, and that's going to be our measure. That is what we are measuring. Maybe you're doing this batch jobs. We're talking about batch jobs a bit earlier. If you run a batch job at 2 a.m. and you need it to be finished by 3 a.m., that is what you're measuring. You're not really measuring how much resources you're using, because at the end of the day, if your batch job runs in 2 seconds or an hour, you're still done in time. So we care about the resources. But that's not our metric that we're measuring to determine if we're okay. We're caring about the impact to the client. So we're going to use an API, HTTP request, because it's nice and easy. But it might be different for your application. What is it that impacts your customer or your client? That's what you want to measure. And how are you going to measure it? So we need to find a baseline. We spoke about sub 1 second response times for an HTTP response. That's kind of a general metric. But you should define an SLA. If you don't have one, define one. Go to your client and say, well, what do we agree on here? And you might want to go further and say, okay, we can use sub 1 second response times, but maybe 99% of the time we'll get that right. There might be one occasional that's like over, and that's okay. We just want our average to be sub 1 second. We need to find ourselves a baseline. How much memory and CPU usage are we using just normally? So if you have in production monitoring, that's a good place to start. Have a look, see what it's like, see what your response times are like. That's your baseline. That's where we starting off. Today, I'm going to run an application just locally, just on my laptop, and you can start with it like this as well, and then run a batch of tests against it. That's how we're going to establish our baseline. See how much impact this stuff has. But you have to compare it to something. And that's what our baseline is. Then our lever. I like to call it a lever. It's our test. What are we doing to our application to measure this impact? We're going to run a set of tests. So I said an API application, we're going to make some HTTP requests. This test or the stress test should mimic what would happen in a real life system. If you have an API and let's say you have 4 endpoints, let's assume all 4 endpoints get hit. Hit all 4 of those endpoints, and now with our stress test, we're going to kind of, push this up to quite a high load, which again should be in line for SLA. If you're expected to maintain like 10 requests per minute, that's what it should be. Maybe it's 10,000 requests per minute. But having an SLA gives you an idea of what you should be setting the stress test to. Again, if you don't have an SLA, this is a good time to establish that. You can tell your clients, I can hold 1,000 requests per second. I've now done the test to prove it. This is now our agreement. And if something falls apart, well, at least we have something to fall back on. This was the agreement that we had. Maybe we need to make changes depending on what happens. And then when we're testing this, we want to try and mark as many third parties as possible. A nice library for this is something like Musketeers. You can mark API calls quite nice and easily. Today, I'm not doing any third-party calls, so easy for me. But I'm using a database. And to keep the test as clean as possible, I'm just cleaning the database at the start of every run. So I'm using that lovely create drop option in Sprint. So it keeps it relatively real, but yeah. Marking the database, I wouldn't do that. Maybe just drop the database between your tests. Might be easier. Okay, so today I spoke about the application I'm going to use. I wrote a simple API that I'm going to use to benchmark the stuff against. I use Spring Boot, I use Webflux, and I added a couple of nice libraries. So I'm using Actuator to keep an eye on what's going on. I've got Kubernetes there. I wanted to talk a bit about Kubernetes a bit later on. For my first couple of runs, I'm not using Kubernetes. And then Grafana is great for visualizing what's going on. To test the actual application, I'm using Apache JMeter. What this is it's an Apache project that you can build up a test bed using this UI, and it is able to just fire all these HTTP requests against your application. So there's quite a lot here, but it's relatively simple. You create a test plan, you define a couple of variables. I didn't use it in too much detail. There are some nice guides out there, they kind of really complicated, but it's not that hard. The key thing to keep in mind though is we care about how many users we have, active concurrent users, and we care about how long this test is going to run for. So number of threads of active users is not like how many requests per second you can handle. Because if your application responds in like 100 milliseconds, that one thread can serve 10 users. So 10 threads or 10 active users is 10 people like hitting the enter button at the exact same time. So 10 is a nice number to start with. Maybe you want to go to 100. Maybe you don't even want to do up to 10. It's up to you. You need to find out what it is. And again, I refer back to the SLAs. It depends on what your agreement is. Using this, you can then see how many requests per second you can actually handle. And this JMeter does produce some very nice diagrams to show you like how many users you're able to, how many requests per second you're able to serve. And then lastly, I want to talk about the duration in seconds. The duration of a test, especially in a Java context, it matters. When your application runs, your JVM starts up and it's spraying instantiates with beans, lots of stuff's going on. But then when you start actually running your code, the JVM is able to identify hotspots and it will optimize the code on the fly. So maybe your first request could take 1 second, but your 100th request will take like half a second. So duration matters. I've used 5 minutes or 300 seconds here, and that's good enough from my point of view, but you might want to run your stress test longer to see what happens. What happens to those response times? Because that's what we measure. We care about response times. What happens to those response times as you go further and further throughout the test? Because if if this graph is going like crazy, maybe you haven't plateaued yet. And then once it starts to plateau, then you can start to see, okay, now we know we're at a stable point. Because I'm pretty sure when the application is running production, they're probably running for days, weeks, or months. Hopefully not just like a couple of minutes between restarts. So pick the time frame that makes sense. Cool. And then this is just kind of like what the request looks like. I'm only showing one because it's rinse and repeat really. You just define the request that you're going to make. And the last thing I want to mention is, for our test, I consider a test successful if every single HTTP response is success. If one fails, it means that something's gone wrong. I'm making the assumption the system works. So if I get a failed response, it's the resources that have impacted the system, and we need to make adjustments to the resources. So the first one that I did, I ran just bare metal on my machine, and I analyzed it using Visual VM. Visual VM is a very nice little plugin, and I'm not brave enough to do live demos, so I made a screen recording. So let's see if this works. All right, so I wanted to profile the startup of the application. So when Spring Boot starts up, it uses a lot of memory and resources straight off the bat, what it instantiates for your beans and stuff like that. I'm technically not profiling the application. I just want to see what its resources are, but this gives me a nice view as to what is going on under the hood. It's using a Java agent to get these resources into Visual VM. So copy that, get across the command line, paste it all in, and run the application. Once the application starts up, it starts sending these metrics through to Visual VM. And then straight away, I can head across here, and I can start to see what my memory usage looks like. Now, take note that there's 2 tabs there. There's heap and there's metaspace. For now, I'm just talking about the heap memory. I'll dive into a little bit more later. But yeah, Okay, jump ahead, it's fine. This is my baseline response. So I ran the test, ran it for 5 minutes, looked at the amount of memory used, and let's see if this works. All right, so here you can see that we're topping out close to a gig of memory. We're not using all that memory, it's just the heap space that is available at the moment. But if we have a look at these peaks along here, we're peaking out around 800 megabytes. So you might think, okay, that means I need 800 megabytes for this application to run. That's quite a lot of memory for quite a small application. So, well, I took a guess, and I'm going to halve the memory, put it down at about 512. And well, interestingly enough, suddenly I'm not getting close to that 1 gig that we had before. I'm now using just over 250 megs. So, and again, so I was like, all right, let's halve it again, let's see what happens, 256, and again, same thing again. What's happening here is the JVM is very good at using the resources that it has available to itself. So if it has no limits, it's going to use as much memory as it can, because it's easier to allocate more memory than to wait for the garbage collector to clean up old memory and recycle it. But as you start constraining the memory, it will allocate memory up to that point, and then the garbage collector will recycle memory within those limits. So if you give it 512, it will probably use 512. If you give it 256 here, well, it'll try and use as much of that as possible. And then garbage collector will come in and start recycling memory. And again, we dropped it down to 128. I did drop it down to 64. 64 didn't run, it crashed. So we kind of know a little bit now, 128. But I did mention that this is just a heap space. So when I was running it basically on the bare bones laptop, it's very easy to limit the heap space. But there are a lot of different types of memory that the Java application uses. You've got heap space, you've got meta class, and all types of things. So if you are running your application outside of the Docker context, it's probably going to try and use your entire system. You may want to play around with those settings to get it right. I'm talking Docker, so I'm going to head straight into Docker now. Okay, let's look at results. So I jumped in here. So if you look at these results, you'll notice something quite interesting. I changed the amount of memory that was being used, but the response times on average basically didn't change. And that's pretty much because it doesn't matter how much memory the application has. If it has enough, it will still run. And it doesn't have too much impact on the response times, which is quite nice. So I'm going to head into Docker now. I want to show a couple of tools that I would recommend you guys have a look at. So firstly, I'm running this using Docker Compose. Locally, I find it the easiest way to simulate a Kubernetes environment because I don't want to run multi-class development. Maybe you do. It's up to you. And I'm going to limit the resources using these fields over here. This is a Docker Compose version 3. I know this is version 2s and version 3s. I think get confusing. So basically, I'm going to give it some memory. I'm going to CPU, run it, see what happens, reduce it, carry on top of it. I'm going to keep an eye on what's going on with cAdvisor. Very nice little service that Google provides. They get very nice graphs, and that's quite nice. The one downside of cAdvisor is that it's very good for seeing what's going on at the time, but going back afterwards, I don't know if it has persistence or not. So it's great for seeing what's going on while you run your tests. But better options, perhaps, Prometheus, Grafana. So you've heard of them. Grafana is fantastic because you can just go online, find a dashboard template, import it, and voila, you have a dashboard. And you can have a look at the nice graphs. And between Prometheus and Grafana, it gives you very good metrics of what's going on. So you can see how your application is using your memory and your CPU. So I ran the tests, and I started with memory, started with a 512 megabytes. Now, the slight difference is that this here is a 512 megabytes of the entire container. So we're not just talking heap memory now, we're talking about the entire container. So it's a bigger constraint. And I worked my way down, kind of halving, until I got to the point where it no longer ran. Well, I got failed HTTP responses. So 110 megabytes was pretty much the least amount of memory that I could give my application for it to run successfully. Reducing the memory did not significantly impact my response times. So That's a win. CPU, on the other hand, well, that's a completely different story. There's almost a linear relationship between how much CPU you give the application and the response times that you have. The baseline and 500M, so 500M is half a CPU or 500 millicores. They're quite close together. So you have diminishing returns when you give more CPU than what is necessary. So if you have a look at our 1 second response time, I can see that 125M, it's not a bad number, maybe 250 is the number to go for. But it was relatively straightforward to get these approaches. Docker Compose, work those values down until you get to the point where you no longer need any SLAs. And then GraphVM. GraphVM is fantastic. On their website, they say run Java faster. And that's basically what it is. They compile Java code, Java bytecode into machine code, which is now can run natively. It builds native images. And with Spring Native, you can build a native Docker image as part of your build. So it's really easy to make use of this technology. The best benefit of GraphVM that I've seen is your startup times. If you've ever watched the startup time of a Spring Boot application, it can take a long time. And when you start constraining your memory and your CPU usage, well, it can take up to 2 minutes, sometimes even longer. I've seen our applications take up to 5 minutes with, we didn't quite set those values right, but it can take a really long time. GraphVM, we're able to drop our startup times down to a couple seconds, which is huge. And I spoke earlier about auto-scaling. If you want to auto-scale your application, and it takes like 2 or 3 minutes for the application to start up, that surge in users has probably passed by the time your application starts up. So it is definitely worth having a look at this. It is worth noting, though, that there are some situations where GraphVM doesn't work. It should work in almost all situations, but if you're doing some special like annotation type processing and runtime, you might encounter errors. But give it a shot, you might as well do it. Cool, so I ran Spring Native, same set of tests. And this is what we got. It's very similar results. Memory, as long as you have enough, it doesn't really impact your response times. But CPU, a slightly different picture, but still relatively similar. 125M, which is the one that I was looking at earlier, is still maybe the one that we want to look at. It was able to run on far less memory if I didn't care about the response time. So, 16M CPU. So it could use far less CPU usage if I didn't care about the response times, but I'm not sure if that's a suitable compromise there. Comparing what are the results? Well, obviously running on my laptop with no constraints, it's very fast. I think it's got like a ton of memory, lots of CPUs, not really fair context. But comparing native and Docker, these two graphs here is using the same amount of resources, CPU and memory. Both of them, for the most part, do fit our SLA, with the majority of responses being under 1 second. But the next one is a little bit more reliable. So my conclusion here is that I want you guys to be able to go out there, run your applications, benchmark your applications, and see if you can find the right CPU and memory values for your application. If you get these values right, you can save your client money. You can use some of the auto-scaling capabilities of Kubernetes, and you could even potentially handle more requests. Give GraphVM a try Spring Native if you want. But yes, give it a shot. Do it yourself. Cool. Thank you for listening to my talk. Cool. Any questions?
Was there any impact for the test you ran for memory? What CPU did you give it, and for the CPU, what memory did you give it?
So the first run that I did, when I was testing the memory, I kept the CPU constant and I dropped the memory down to the point where, like the minimum. Then I picked a memory value that worked. So let's take 128 megs. And then I dropped the CPU usage down to the point. And this is the pragmatic approach, because you could go and do a little bit here, a little bit here, a little bit here, and kind of work your way until eventually you find that perfect point. But that could take a lot of time. The impact of dropping down the CPU when you have limited memory is your garbage collection can now take longer. So it is worth noting that when you limit your memory, your CPU does get impacted.